Okay. So before we starting in our materials today, guys, do you have any question from the previous class? Any questions?
Any questions for what?
From the previous class, the materials of previous class, or any question
No,
related to the course?
So far, no.
Okay, good. Okay, so just let me remind you very quick. Okay, so last class we discussed the decimal, binary, hexadecimal numbers, and we discussed the how can we convert from one type to another. Okay, and also we discussed what the meaning of ASCII code, and also discussed the digital basics and the data levels for input or output data according to any kind of ICs. We have active high and active low, and this would be changed according to the IC type. And also we review the logic gates, the different logic gates, and we could see how these logic gates can be used to make some arithmetic operations like adding, for instance. And for sure, adding will be repeated many times in order to make a product or multiplication. And the same is also for subtracting and division. So these are what we have discussed in terms of the logic basics or arithmetic operations. And also for sure we can do logic operation by using these logic gates. So we can do both arithmetic and logic operations using logic gates. Also, we started discussing the memory. Okay, I believe, yeah, we started discussing the memory in the previous class. So we said that, let me put the pointer here. Okay, yeah. So we said that the minimum size for memory is a bit. So bit can store either 0 or 1. So it's only 1 digit. If we have 4 digits, we can call it nibble. If we have 8 bits, so this would be a byte. If we have more than byte, we can have like word. So word can be 2 bytes, or even sometimes more than 2 bytes. Okay, so these are the well-known units of memory we are going to use. So we reviewed also nibble is 4 bits, byte is 2 nibbles or 8 bits, kilobyte is 2 to the power 10 bytes, which is 1024 bytes, and megabyte means 2 to the power 20, which is 1024 kilobytes, or this number in bytes. Okay, and gigabyte is nothing but 2 to the power 30 of bytes. So this can be the units for storage, guys, either for memory or for other storage devices. Like for instance, in computers, in personal computers, we have hard disks. So hard disk can store data as well. Okay, and with the same sizes or with the same units of size. You can see several hard disks in several terabytes. Terabyte is 100 or 1024 gigabytes. Okay, so this is higher, but it's not included here. So terabyte is 10 to the power 40 of bytes. Okay, and also we discussed that we have 2 different types of memory, like RAM, which stands of random access memory, and we have ROM, which is read-only memory. Actually, the names are not figuring out these type of memories nowadays, because it has been developed many times. For instance, for the ROM, can you imagine that your flash memory, your stick flash memory is a ROM, but it's an advanced type of ROM. So it's not read-only. You can read or write. You can erase the data and rewrite many times, millions of times. Okay, so read-only memory became totally different compared to the first memory, which is ROM or read-only memory. Okay, so we have many advancements in this type of memory. However, the RAM is still RAM, which is random access memory. RAM is a volatile memory. So if you interrupt the supply on RAM, every data stored in RAM will be disappeared. However, data on ROM will be available all of time. For that, guys, we use ROM in order to write codes. Code means your program, which is going to be used in your controller, should be written on ROM, not on RAM. And RAM only can be used in storing data during the execution of your program. Okay. Any question, guys, regarding RAM and ROM for now? Okay, good. Then we started discussing the internal organization of your computer. So for a personal computer, in order to have some operations, some controls, we have some things connected to our CPU. So CPU is central processing unit. What's inside CPU? This is what we need to investigate in our course. So CPU is our central processing unit, which is including inside a processor, along with some registers, and we will discuss these in details. And in order to make like complete computer unit, you still need some other devices or some other equipment like RAM and ROM. So ROM in order to store our operating system, like Windows, for instance. RAM in order to store data during the execution of any kind of program. Hard disk is used to store data. CD and DVD, we discussed this. This is not used anymore in new computers, but it was available since, I believe, a few years. And it was very huge development in storing data at like 1995. So at that time, the invention of compact disk was very huge compared to our former floppy disk. So floppy disk is very small size and can load the data easily compared to the compact disk. But as we discussed now, flash memory became very interesting compared to this type of storage memory. So you cannot find anymore the CD or DVD. Also, in order to entering or get data out from the computer, we need some input-output devices. Input-output devices like what? Like, for instance, printer. So printer can print out some pages, some photos, some letters, whatever, the data. So this is considered as output device. For instance, scanner can be considered as input device because it's going to scan any document or photo from outside world and enter these data to computers. So this is considered as input device. Keyboard, we can use keyboard to write anything. So this is going to be input device. Speaker, so speaker is going to give us the sound coming from the computer. Okay, so this can be considered as output device. Camera can be considered as input device. Mouse can be considered as input device. Monitor can be considered as output device. But for now, for instance, touch screen monitors can be considered both input and out because you can select also using the screen. So these are the different components we have in our computers. We may have more equipment or devices connected to our computer according to our needs. So mainly we can divide our equipment to memory, storage, okay, and input and output along with our CPU. Now, guys, in order to communicate between all of these equipment, we need something called bus, okay? What is bus? You know, in the computer, you have what's called motherboard. You know the motherboard, guys? Did you open any personal computer before? I mean, the case of the personal computer. Did you open such case before?
Yeah, I have.
Okay, let me give you just one photo for a motherboard in order to recognize what the meaning of motherboard. So I didn't open Google Map just to go this. Okay, it seems internet is very slow because of the Zoom meeting. Okay, it seems it's not easy to make some search. Can you hear me, guys? Hi. Can you hear me?
Yeah, I can hear you.
Okay, so it seems just that the browser is not performing well while we are doing Zoom meeting and recording. Okay, so motherboard is like printed circuit board, and it includes all of the wires or tracks which are connecting all of devices together. So we can refer to the tracks on the motherboard as bus system. And we will discuss now in more details what are the different bus systems we need in microprocessor. Okay, so this is internal organization of computers. Any question, guys, in this slide? Good. Now, let's elaborate more in bus system and why we need bus systems in our processors or computers. Now, guys, we can make many types of buses according to our needs. So we have here what's called address bus. We have something called data bus, and some others called control buses. Anybody knows about these bus before, guys? Can anyone discuss what the meaning of, for instance, address bus or data bus? Okay, let me discuss it from scratch. Now, can you imagine we have here, along with the CPU, we have RAM, we have ROM, we have printer, we have some storage disks, we have monitor, we have keyboard. If you would like to get some data out from the CPU to, for instance, print it out. So this line here, let me bring the pointer. Yeah, this line here, guys, represents the data bus. So if the data bus is moving here, not only the printer can see this data, however, all of input-output devices can see this data. Is it making sense? Okay, so how can we identify our device which should be contacted to take this data? Otherwise, all other devices will take the data by mistake. In order to do that, we have to define another type of bus system, which is address bus, and make this address bus selecting the address of the device we need to communicate with. So if I would like to transfer data from the CPU to our printer here, I can just give the address of printer. And in this case, this data is going to be transferred to this address only, not from all other addresses. This is one thing. One other thing is, for instance, in disks, like hard disk, or in RAM and ROM. For instance, in RAM, RAM is a memory that you can read or write. So you can read data from RAM and you can also write data on RAM. So if I define the address of RAM, and we have here some data, so should the data go to the direction of reading? So the RAM should read the data, or we can say processor should write on RAM, or it should be the opposite, data coming from RAM to the CPU. So in case of bidirectional power, a bidirectional data flow, we have to identify the direction of data. Otherwise, we cannot recognize if this data is input or output. Definitely, we can do that by means of the control bus. So the control bus can say or can order the RAM to read or write according to our needs. So if I would like to read from RAM, so we should activate the read line. So read line, for instance, assume this is read line. So we're giving a signal through read line. This means the data is coming from RAM to our CPU. Otherwise, if the data is write, so this means the data on the data bus here would be written on RAM. So this is the way, guys. So in order to flow the data between devices and the processor, we need to have three different types of bus. We need to have address in order to identify the device that we need to connect. We need to have data bus for sure to transfer the data either from processor to other devices or from devices to processor. And also we need to use control buses in order to control the data flow. Is it going to be from CPU or to CPU? Any question, guys, in this part? So let me ask you a question now, guys. If I would like to use monitor, which type of buses we need? What do you think? Can you hear me, guys?
Data bus, probably.
Data bus, so we have to use data bus. What else? Do we need to have address bus or not?
Yeah, I'd say.
We have also to use address bus. And for control bus, do we need control bus to write on memory to see the data on monitor or not? What do you think? So in my opinion, for the monitor, you just need to read data from monitor. So it's not important to have control bus for the monitor. However, if the monitor going to be touch screen monitor, which is going to take some data from outside, so in this case, we have to identify reading or writing. So we will need control bus in this case. Okay, guys? Okay. So this is regarding the bus system we have in any kind of microprocessor system. Now, one important thing we need to figure out is our memory, how the memory is organized. So memory, guys, if we can give an example of memory, like if you have a note. So for any note, you have many pages, and each page have some lines you can write on it. Okay, just small note for instance. So we can assume our memory is typically like a notebook. So the notebook has a lot of pages, and each page you can write some data. And in one page, you have many lines in order to write your data. The same is the organization of our memory. So can we assume now if we have one page of memory, so assume this is one page for instance. So during or in this page, we have many lines. So we can call the address of the first line as 0. The second line is 1. Third line is 2, and so on up till getting many lines per one page. So in this case, guys, in order to identify the line we need to read or write data, we have to identify the address of this line. How can we identify the address of this line? We should have some pins for the memory, and these pins would giving some signals in order to recognize the address of any line we need to read or write. So for instance, if we have page of RAM, and this page, we have like X lines assigned for this page. So assume X equals, for instance, 3. So we have 3 bins, and these 3 bins are going to be used as address terminals for this page. So in this case, we expect to have number of lines, which is 2 to power X. So 2 to power 3 equals 8. So if we have 3 pins for address in this page, we would have now 8 lines per this page. Is it clear, guys? Is this example clear for you? Shall I repeat it again? Please let me know. Is it clear, or I can repeat it in another way? Huh? Okay. So let me repeat it one more time, and I will ask you if it is clear or not. So again, guys, if we have 3 pins, assume we have an IC. So I have an IC with here, let's say 2 pins instead of 3 pins. So bin A and bin B. In this case, how many lines we can use in this page? So this is 1 page of RAM. How many lines we can use in this page if we have just 2 pins?
4 lines.
4 lines. How did you get it? 4 lines.
2 to the power of 2.
2 to the power 2, which is the probability of having data using just 2 lines. So assume I have A and B. What are the probabilities? We can say 0, 0. We can have 0, 1. We can have 1, 0. And we can have, last thing is 1, 1. Let's say here 1, 1. So we have now like 4 different lines, or we can contact 4 different lines if we have 2 bins. So this means for this kind of page, we may have now like 1, 2, 3, 4. So this is going to be line 0. This is going to be line 1. This is going to be line 2. And this is line 3. So we have now 4 lines since we have 2 bins address data, or 2 bins address lines. So if we have X bins address lines, we can have data lines of 2 to power X. Is it making sense for all now? Please, if it is not still not clear, please let me know. So now we have lines of 2 to power X. Assume we have only 1 bit can be written in 1 line. So what would be the size of our page here if we have just 1 bit per line? So what would be the size in bit, the size of the memory?
Could you repeat the question?
Again, I will repeat the question again. Now we have 2 to power X lines, or let's make it on that simple example here. We have 4 lines. If you have 1 bit size for each line, so which means you can store just 1 bit at each line. So what would be the overall size of our page now? I mean the size of memory. It would be 4 bits only. Is it making sense? Because you have 4 lines and you can store 1 bit at each line. So the overall size now would be 4 bits. Is it making sense, guys? So if we have now lines of 2 to power x, and each line would store just 1 bit. So how many bits we have in all of this page?
4.
For this one, for the 2 to power x lines. 4 bits in this small example, because here we have 4 lines, okay? And each line can store just 1 bit. So we have overall storage of 4 bits. But in case of having 2 to power x lines, so how many bits we have in this page?
Would it be 2 to the x bits, since it's 1 bit per line?
Right. So we have now 2 to power x bits. But most of memory, guys, we don't have just 1 bit per line. For most of memories, we may have 1 byte, and sometimes we may have 2 byte or higher. So in case of having 8 bits in one line, which means 1 byte. So what would be the overall size of this page now? In terms of bits, it would be 8 times 2 to power x. This is in bit. Or we can say 2 to power x bytes. Is it making sense, guys?
For me, yeah.
Okay, good. For all, please, if you still confused about this, let me repeat it. I can give another example. So for now, guys, we agree that if we have 8 bits per one line, and we have 2 to power x lines, the area or the size of this memory would be 2 to power x times 8 bit, or we can say 2 to power x bytes. Okay, so as you can see here in this example, the entire chip will contains 2 to power x times y. So if we consider y as the width of data, so this would be now 2 to power x times y bits, okay, where x is the address bins and y is the number of data bins on this chip. Number of data bins is similar to number of bits, because each bit needs 1 line of or 1 bin in order to be connected to this memory. Okay, guys. So let's see one example here for a memory. So for instance, here in the left-hand side, we can see one chip. We can see one chip of RAM, and it's written here 128 times 8. And we have 8-bit data. So this means, guys, 8-bit data. So this means each line will have 8 bits or 1 byte. In this case, how many lines we have in this RAM? What do you think?
7?
Not number of bins.
Or,
The number, sorry, the number of lines.
oh, and
Number
would it
of
be
lines.
2 to the 7?
2 to power 7 exactly, which is 128. So since we have here 128 lines. These 128 lines can be configured by means of 7 lines. So we have 7-bit address from AD 1 1 to 7. Okay, 7-bit address just to identify the address line within this page. Okay, and we have 8 bits per line. For this IC in the right-hand side, you can see here, figure 11 here, we have 2 kilo times 8 SRAM pins. Times 8, all of time we refer to the number of bits per one line. So this means it's 8-bit data type. This can be figured out from the input-output data. So let's check the input-output pins here. You will find IO 1, 2, 3, 4, 5, 6, 7, 8. So we started from 1, we end at 8. So we have 8-bit data. So this is the number of bits per each line. Now, 2 kilobyte. Sorry, 2 kilo. 2 kilo here is referring to the number of lines. So 2 kilo means 2 to power. Do you know what's 2 kilo? We said 2 to power 10 is 1 kilo. 2 to power 10 is 1 kilo. So 2 kilos is 2 to power 11. So if we have a look here to our address bus, which is started here from A0 to A7, then 8, 9, 10. So you can see here we have 11 lines for address. So this is making sense now for us. We have 11 lines for address. So the number of lines that can be communicated is 2 to power 11, which is 2 kilos. And each line is 8-bit. So this memory chip is 2 kilobytes. Is it making sense, guys? Any question on this part? Okay, good. Now, the question is, do you know what is the size of memory in your personal computer? How much memory you imagine we may have in our personal computers? Let's return back again to our memory here. Okay. So did you check before? Please, guys, if you have any question. Okay. So this is the answer of that question. Yeah. 16 gigabyte. Okay, nice. So please, guys, instead of writing, because I have 2 screens and I just looking for the screen which I'm presenting with you. So please don't write in a chat. I do prefer to just open your mic and speak with me. Okay. If you don't have mic, so please, anybody can let me know if there is any message on the chat. Okay, guys. So 16 gigabyte. Can you imagine now, like 1 page of RAM is just 2 kilobytes. So in order to have many or huge memory, like several giga or 16 or 32 or like that, you need many pages of RAM. In this case, our example regarding represented RAM, I said in the beginning, we can assume that RAM is like a notebook, and each in the notebook we have many pages. So the RAM of the several gigabytes can be many pages like a notebook. Okay, and we can communicate with the address lines, which is giving here, for instance, from A0 to A10. These are the address of lines just within 1 page. But in this case, in order to reach out to all of pages or the addresses of all of the memory, you have to have some lines to identify the address of the page firstly. For instance, I cannot say to you, open the textbook at line number 10. I have to identify the page firstly. Open your textbook at page, for instance, 11 and see line number 10, like that. So it would be the same also if you would like to speak with memory. We need to identify the page number. For these guys, we need to know what the meaning of address decoder. Address decoder. What is address decoder? Address decoder is a device that can be used to get more addressing lines from few address lines, which means if we have many devices, not only for memory, if we have many devices like input-output devices, like RAM, like ROM, like printers, whatever, and we have just a few lines of address bus, we can extract this using address decoder. So this IC here is representing 3 input, 8 output address decoder, which means you have A, B, and C address lines. As you can see, if these address lines, assume firstly, these J1 and J2 are used for enable the input data in order to work, okay? Enable the control itself, okay? Assume we don't have G1 and G2 now. Just assume we have A, B, and C. So let's start from this case here. If we have A, B, C, all are active low. So in this case, the output would be active low for Y0 and active high for all others. Now, if you switch the signals between the 3 inputs, you can have active low for 8 devices because we have 2 to power 3 equals 8. So this means we can activate 8 devices, or we can say 8 pages of RAMs, 8 pages of RAM using 3 address lines. So this is the use of decoder if we have chips for some pages, or if you have many devices and you need to contact with one device. So this is called, guys, address decoder, address decoder. So for memory, we may need to have some address decoders. Address decoders are going to be identifying the page number, and other address lines can identify the line within page. So if you have, for instance, this is our IC here, or this is, assume this is 1 page of RAM, okay? So the data bus would be connected to all of pages in parallel. So this would be the first one. We can draw the second one here. So let me just draw here. So we can have another page here, okay? Up to n pages, okay? And all of these data would be going in parallel, okay? And so on, up till the last data, okay? So this is the data in parallel with all of ICs. And then the address bus would be connected also in parallel with all of pages. So we have here also the address bus from A0 up to A11. So this is 12 lines. So the number of lines within page would be 2 to power 12, okay, which is 4 kilobytes. So each page now is 4 kilobytes. So this is 4 kilo. 4 kilo. I said 4 kilobytes, guy, because each line has 8 bits. Okay, so 4 kilo lines times 8 bits, so it would be 4 kilobytes. So this is this 4 kilobyte, this is another 4 kilobyte, and so on. So this is page, and so on. We have many pages. All of data lines are parallel between pages, and now this one would be connected to only this page. And the output of the address decoder should be connected to all of pages. So in this case, we need to add here like address decoder and this is here representing the address decoder for this page. So this is the address decoder. Okay, and according to our signals, we can select which device. Now, for 4 lines, guys, how many pages we can use in RAM if we have 4 lines? Actually, it's written here. So we have from A12 to A16. So we have 4-bit address lines. So this means number of lines of the address of the chips would be 2 to power 4. So we can communicate with 16 pages of RAM. You got it, guys? So now with address from A0 up to A15, which is 16-bit, we can contact memory of 16 page, and each page contains 4 kilobytes. So this would give you the overall memory you have for this RAM. Okay, guys, so this is the way how we can communicate with RAM. How can we communicate? We identify the address of RAM, and after that, we can identify, are we going to read or write? So here, MEMW means write, and MEMR means read. So this means if you have active low signal on read, the data here will be coming out from memory and going to processor. However, if we activate write, so if WR here is active low pulse or active low signal, in this case, the data here is coming from processor and written in the memory, which is already addressed by the address decoder. Is it clear, guys, how we can figure out the memory using address decoders? And how can we communicate with any line in the memory using the address bus? Any questions in this part? Okay. So I'm going to make a small homework for you. Okay. I would like to design a memory of a certain size. I will write that on campus, on eCampus. So follow the eCampus announcements. I will define you a certain memory size, and I would like from all of you to have like layout for the expected organization of this memory. Okay. Any question, guys, in this part? Okay, good. Now, we could recognize the meaning of memory. Let's go now elaborate more inside the CPU in the central processing unit. So for the central processing unit, we have many inside items. We have what's called the flags. We have what's called ALU. We have something called the program counter. We have something called instruction, register, decoder, timing and control. We have registers A, B, C, D, and so on. So let's discuss all of the items we have inside our processor. Firstly, a program stored in a memory provides instructions to the CPU to perform an action. The memory storing a certain code, and this code should give some instructions to the processor in order to perform a certain action. Okay, we are going to give an example after this discussion, like for instance, adding or subtracting 2 numbers or adding 3 numbers, and see the steps exactly performed inside our processor in order to achieve this instruction. So the action can simply be adding data, such as payroll data, or controlling a machine, such as robot. This is one of the control or data we may need to calculate inside a processor. The function of the CPU is to fetch, this is the first word, fetch these instructions from the memory and execute this instruction. To perform the actions of fetch and execute, all CPUs are equipped with resources such as first unit is arithmetic and logic unit. So we understood now in order to execute an instruction, we need to fetch the data from the memory and then execute. But there is one missing thing here, guys, which is between fetching and executing, we need to understand the instruction, which means decoding the instruction. So we will discuss now what's called the instruction cycle. So instruction cycle have 3 main stages: fetching the data, decode this data in order to understand what this data refers to, or what is exactly the instruction need to be executed, and then execute this instruction. So let's start firstly with the first unit, which is ALU, or arithmetic and logic unit. Oh, okay, so we started firstly with the registers. So this is extra word here. We will discuss this later. Starting with registers. The CPU uses registers to store information temporarily. So temporarily means it's not a code. It's not like ROM. So registers are similar to RAM, which is not going to be storing the data all of time. Just we need to store the data during execution of our instruction. So this is register. The information could be 2 values to be processed, or the address to the values needed to be fetched from memory. So this data, guys, which is going to be obtained or stored in a register, can be one of 2 things. Can be address for the place that we need to bring the data, or can be the data itself. So it can be the value we need to process. Like for instance, I would like to add 2 plus 3. So I need to store the number 2 in one register. Okay. Or sometimes the data stored in this register is referring to the address in a memory location, which means number 2 is stored in a memory location, for instance, 01FF. So this is a memory location in our RAM, and we need to bring this number in order to be used in our calculation. So all of time registers will be including or storing either data values, which are going to be used, or address for certain location in our memory. Registers inside the CPU can be 8 bits, can be 16 bits, can be 32 bits, or even 64. I didn't start with 4 because 4 bits are not used anymore. But long time ago, we had 4-bit processors as well. So we can call the processor, guys, by the name or by the size of its registers. So if the registers of the CPU is 8-bit, we can call this processor as 8-bit processor. If the number of bits per register is 16-bit, so this means this processor is 16-bit. You know, our computer processor is 64-bit now. So we can say the registers inside our computer processor is 64-bit. We still have now 32 and 64 for personal computers. Okay, nice. In general, the bigger or larger size of registers, the better the CPU. which means, guys, if you have processor with high storage registers, this means this processor would be better in terms of speed of executing instructions. Okay. The disadvantage of more bigger registers is the increased cost of the CPU. So the CPU of the 64-bit would be expensive compared to the processor of 32 bits. So this is regarding the registers, guys. If we return back to the figure here, these are our registers. All of microprocessor includes a register called A, and we refer to this register as accumulator, okay? And we have B, C, D, and we may have more, okay? So this is these are the registers in the microprocessor. Second item is ALU. ALU is stand for arithmetic and logic units. In arithmetic and logic unit, we can perform all of arithmetic operations like adding, subtracting, multiplication, division, and so on, and even complex arithmetic operation like integration, like differentiation, and so on. And also we can perform all of logic function like and, or, not, XOR, NAND, and so on. Okay, so this is called arithmetic and logic units. Also, we have what's called program counter. Now, guys, if we imagine that this is our memory, so this is our ROM, and inside ROM, we have our codes. So for instance, I made a program to control a robot. So inside this ROM, I should add all of control code, which is going to control this robot. ROM, like any kind of memory, includes data lines, and each line has a certain address. So we can say, for instance, starting from address line 0, 0, 0, 0. So we have 4-line address, okay, up to an address of F, 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 F. So this will be our size of our ROM. And we have many lines inside. In order to execute the program and stored in ROM, we have to have a pointer here. This pointer is referring to the instruction. And after referring to the instruction here, the processor is going to execute this instruction. However, the program counter will increment 1 in order to point to the next instruction. So if the processor, for instance, is executing at line number 3 here, you will find the the program counter is pointing to number 4. Why? In order to execute order or line number 4 after finishing 3, and so on. So all of time, the program counter will point to the command that will be executed after the current instruction. Is it clear, guys? For instance, guys, if the processor is executing an instruction at line number 00F1, what would be the value stored in the program counter?
00F2.
Exactly. Thank you. Very good. So all of time, guys, the program counter would store the value of the address of the instruction that will be executed after the current instruction. Okay, so this is called the program counter. It's nothing but register of pointer. So as written here, the function of the program counter is to point to the address of the next instruction to be executed. As such instruction is executed, the program counter is incremented to point to the address of the next instruction to be executed. So this is simply the program counter. And since, guys, all of time the processor is executing instructions line by line, so the program counter all of time will be incrementing the value inside, not decrementing, okay? Because we have some other pointers decrementing, not incrementing the address. We will see this later when we discuss what's called push-pop instructions in our course. One more thing is instruction decoder. Actually, if you return back here to the figure, you will find we have what's called instruction register, okay, which is instruction decoder, timing, and control. All of this unit, guys, is referred to a control unit. Some books refer to this as control unit, CU. So the main two parts of any processor are CU and ALU. CU is the control unit, and ALU is the arithmetic and logic unit, along with some other registers, like what we said here. We have some registers A, B, C, D. We have program counter. We have flags as well. Flags also are some registers. So, again, an instruction decoder is a part of the control unit. What's the function of an instruction decoder? The function of an instruction decoder is to interpret, which is translating, the instruction fetched into the CPU. What's the meaning of translating this? For instance, you have some instruction, you need to add two numbers. So decoding means the plus sign between the two numbers, it should be figured out that it needs to adding the two numbers together. So this is called the decoding or translating this instruction. So this is the function of the instruction decoder. So instruction decoder is nothing but interpreter for the instruction which is going to be processed or fetched into the CPU. One can think of the instruction decoder as a kind of dictionary. Yeah, it's typically like dictionary, storing the meaning of each instruction and what steps the CPU should take upon receiving a given instruction. For instance, we got instruction of 2 plus 3 equals. So this is our instruction. And for sure, we need to calculate the result. And for instance, moving this result onto a monitor, for instance, okay? So when this instruction seen by the CPU, the decoder or the instruction decoder has to translate the addition instruction. So the addition instruction is decoded by a certain way with a certain code inside the instruction decoders in order to execute the adding operation for 2 and 3. How to perform this operation? The instruction decoder, once understand that he needs to add these two numbers, it will send these two numbers to the ALU and force the ALU to add these two numbers together. So this is the function of the control unit. Okay, guys? So we can say now, control unit, the function of the control unit is to execute the instruction. Okay? This process is called instruction cycle. So instruction cycle can be now divided in 3 main parts in order to execute any instruction. Let's say execute or perform a certain instruction. In order to perform this instruction, we have 3 parts need to be performed. First one is fetching, which is fetching the data from a certain memory location or registers in the microcontroller. Then decoding this data, which is interpreting the instruction. After that, executing the instruction, perform the instructions using RAM, using ALU, using bus systems, whatever the facilities we have in our processor. So we can say, guys, the head of processor is the control unit, which is going to perform everything. All of other equipment in the processor will be used by the control units. Okay, guys? So this is the main brain or main thinking part in our processor. Okay? The instruction cycle requires certain intervals of time to be performed. This is very important. For instance, in our exams, we have certain time for our exam. For instance, let's say 1 hour exam. So 60 minutes. According to the exam, not all of people can solve the exam at the same time. Maybe if one student is very fast in writing, he can write faster, okay, and finish the exam in very small time. And may others need to think for a long time before of taking the decision of writing answer. So this may take more time compared to his colleague. So now, guys, executing the instruction will depend on many things. How long time we are going to execute to consume in order to make fetching data, decoding data, and execute this data. So this is related to a certain standard time for processors supplied by a certain device. We will discuss it later in the interfacing circuit called crystal frequency oscillator. So this oscillator is giving some pulses, some high frequency pulses, and the instruction would be executed in a certain time of these pulses called the machine cycle. Okay. So this is the time which is required to execute any instruction. In order to recognize that, guys, let's have example to see how the processor is executing instructions. Assume that we have like 3 registers, A, B, and C. Sorry, or 4 registers, A, B, C, and D. And it has an 8-bit data bus. So this means each register is 8-bit, and a 16-bit address bus. So the address bus is 16, which means we have number of lines of 2 to the power 16. And the data for each line is going to be 8 bits. And we have registered A, B, C, and D. The CPU can access memory from address 0000, this is the first line, to address FFFF, and for sure this is hexadecimal coding. So this is now the maximum length. FFFF is the maximum length of, or the last line in our memory, for a total of 10,000 hexadecimal locations, because we started already from 0. The action to be performed by the CPU is to put hexadecimal value 21 into register A. So this is the operation we need to execute now, guys. We would like to store in register A, we would like to store number 21, and then add to register A the value of 24 hexa and 12 hexa. So we have register A, we need to store 21 in register A, and then adding to register A the values of 42 and then value of 12 hexadecimal. How can we perform this process, and how the processor is going to execute these instructions? Let's see that together. In order to do that, let me just discuss fastly with you the code written by, actually it's not the code, it's just referring to the code written by assembly language. So this is not assembly language now, but later we will know the assembly language and translate this to C as well. Okay, so the necessary steps to perform this code can be described as follows. Firstly, I would like to move value of 21 hexadecimal into the register A. For instance, this can be executed using a code B0 hexadecimal, which means if you would like to move a data into register A, the code of this instruction is B0. Okay, or the code will be translated as B0. So this is our code. And the value which is going to be stored in register A is 21. So this is the code and this is the data. After that, in order to make addition, add value 42 to register A. So the code to add a value to register A is 04. So this is the code of addition. So we can say that now 0442. So if you write the code like that, it will be understood that 42 should be added to the value inside our A register, which is 21. So adding 42 to 21, this would be the value in your registers. Then we still need to add one more value, which is 12. So add another value of 12 to register. We said that 04 is our code to add to register A. So we will repeat this again, 0412. Is it clear, guys, what the meaning now of these instructions? You have any problem in understanding the code now? So this code is nothing but, firstly, storing value 21 in A, then adding, this code means adding value of 42 to register A, and then adding also value of 12 to register A. So this is the operation which should be made now in our processor. In order to do that, let's see how the processor is going to implement. If the program performs the actions listed above or listed in the previous slide, is stored in a memory location starting at this memory location. So we will assume a starting address like 1400. So this would be 1400. So how can we write the code in this memory? Firstly, we will start with getting or moving the data into register A. So at this address line 1400, we will say B0 code for moving a value to register A. So this would be written in the first line. It will be understood that the next line should include the value. So when you increment 1 now to go to the next line, 21 would be the value moved to register A. So it will be recognized like that, guys. So once the processor starts saying B0 here, means he needs to store data into A. And what would be this data? It would become immediately in the next instruction. So the value of 21 will be understood as a value. It's not a code. So this is very important. So let's return back again here. We said this is code and this is value. What the difference between code and value? Code means it will be translated to a certain operation. However, data is a value. Whatever this value, it will be stored in that location or will be executed. Okay. So again, if we go back here again, the data which is written in this address 1400 is referring to a code. But the data written at this line 1401 is referring to the value which is going to be stored in 21. Is it making sense for you guys or something is confusing? Okay, if you didn't understand that from the first line, let's see from the second line in order to understand. The second one, let's return back again here. We need to add value 42 to register A. And the code of adding value to register A is 04. So expect firstly to have an instruction of 04 in the upcoming line. And the line after should include the value of 42. So if we go to the program again, so 04 here at 1402 is referring to the code, which means adding a value to register A. Then the line after at 1402, sorry, 03 will include the value which is need to be added to register A, and so on. So we need to add one more value. So 04 here means this is code, and 12 would be the value added. Finally, when we finish the program, F4 code is for halt. Halt means it's finished. So the program has been finished. Could you see now, guys, what the meaning of or how we can execute the program inside the microprocessor? So we may have two different types of data now. It can be a code, which is referring to a certain operation in our processor, like adding, like subtracting, like moving. And it could be a value. Whatever the value, it will be stored as it is in our registers. Okay. Any question, guys, in this example? Good. I have a question for you all. Now, suppose that the address 1403 in our program here contained the value 04 instead of 42. How would the CPU distinguish between data 04 to be added and code 04? Again, the question, suppose the address 1403 contains value 04 instead of 42. Let's go to 1403 again. So 1403 here contains the value which should be added now to our register A. What would happen if we add here 04 instead of 42, guys? What do you think will happen? Is it going to be considered as code or value?
As a value.
As a value, exactly. So in this case, we would add only 04, or we adding 4 to the value in register A, which is 21. So the result would be 25. Okay, so it's not going to be understood as a code. Why? Because the line before this line immediately was a code. So this would be the answer here. So the answer, the code 04 for the CPU means moving next value into register A. Therefore, the CPU will not try to decode the next value. It will use it exactly as a value, not as a code. So it simply moves the content of the following memory location into register A, regardless of its value. Okay, guys, is it making sense now? Okay. Now, we could understand that in order to execute any instruction, we have many tasks. We have to fetch the data from memory, then decoding this data to understand what would be the operation. Is it going to be logic operation, arithmetic operation, moving data, whatever the type of coding, and then execute these instructions. If we have now clock of a certain frequency or pulses, we would execute some pulses or some time to perform all of the instruction. We have two different architectures for executing instructions in microprocessors. One is called Neumann and one is called Harvard, or von Neumann and Harvard. Let me elaborate more in this, but on the frequency oscillator like that. So for instance, if you can see here with me, here we have clock of certain frequency. And as can you see here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are 12 pulses or 12 cycles. So we have 12 cycles of a clock. If we go to the processors of 8051, the family of 8051 processors, we can find that the instruction would be executed in one machine cycle, which is 12 clock pulses. So it needs 12 clock pulses just to execute one instruction. Let me go again now to discuss this in von Neumann here. So as you can see, we have input, We have our control arithmetic logic, and this is a CPU, and we have memory on it, and we have output. Now, if you would like to use an instruction like, for instance, adding 2 plus 3. So let me again, sorry. Yeah, 2 plus 3. So firstly, the processor will add 2 in a register. Then it will decode the plus to the adding operation. The plus sign will be decoded to a certain code, which will allow arithmetic and logic unit to make adding. Okay, and 3 would be stored in another register. So now, guys, we have some data. This data can be operation or some data here, or code and data, or code and value. And we have also some memory locations. The memory location which will store the value of 2, and the memory location which is going to store the value of 3. In the Newman, it has only one memory for all instructions and data. So this would consume more time, like the one which is used in, for instance, 8051 family. It consumes 12 pulses in order to fetch, to decode, and execute. However, the Harvard architecture is different. We have here instruction memory and we have data memory, which is going now to execute in parallel lines. So while fetching the data, we have some other memory or instruction memory which will decode the meaning of plus sign. So it's not going to be executed in parallel, sorry, executed in series. It would be executed in parallel now. So this means instead of having our instruction cycle moving for all of this long time, it would be less. So we have some processors that can consume less machine cycle or less time for machine cycle. Like, for instance, this family of microprocessors. So it can consume 4 pulses to execute 1 machine cycle. And we have more advanced, we have some processors which can execute the overall process of an instruction cycle just in 1 clock cycle, guys. So if we compare the conventional microcontrollers, like the family of microcontrollers 51, like 8051 and its series, it consumes 12 clock cycles for making 1 machine cycle, which means, guys, if you have a processor of 12 megahertz, the processor, sorry, the clock should be divided by 12. So it would be just 1 megahertz. So this means 1 machine cycle will consume 1 microsecond. And if the instruction need to be executed in just 1 machine cycle, in this case, the time of executing 1 instruction would be 1 microsecond. Is it clear, guys? Let me repeat again. Let me repeat this part again. Now, if we have processor of 8051, for instance, any kind of 8051 processors, this is one of the Atmel processors, all the Atmel processors. 1 machine cycle consumes 12 clock cycle of our frequency oscillator. So if we have frequency oscillator of 12 megahertz, 1 machine cycle needs 12 pulses. So 1 machine cycle will need 1 microsecond if it is 12 megahertz. Is okay? Is it clear, guys? However, for faster microcontrollers like this family and like AVR as well, which is going to be described in our class this year, it would consume only 1 clock cycle, not 12 like in the 8051 microprocessors. So in this case, This means the instruction would be executed in 1 divided 12 microsecond. So the AVR processor is 12 times faster than the 8051 processor if the instruction is going to have just 1 machine cycle. Is it making sense, guys? Any question in this part? Is it clear? Okay, so this is called, guys, the different architectures of microcontrollers. In our class, we are going to consider the AVR processor, which is going to consume just 1 clock cycle for each instructions. Okay, so this means it's 12 times higher than the old processors like 51 or 8051 families. Okay, our processor, which is going to be used in this class, is familiar in the market with the name of Arduino. Okay, so from the next class, we will start discussing more in details in the facilities we have in this processor. Okay, and go in more deep information regarding the different input and output ports, the facilities we have in such a microcontroller. Any question, guys, for the materials of today?
Not yet.
Okay, I recommend all of you to study these materials today. So I almost finished the complete introduction given for this course and the first chapter in our textbook, which is called chapter 0. And I'm going to share some materials with you from this book. I forgot to send it from the previous class, so sorry for that. I'm going to share this with you today, and you will find all of these materials today. By the way, would you like me to save the notes I have written here in the file and share it with you on the campus?
Yeah, that'd be great.
Okay, so I'm going to save all of notes I have written here and update the file for you. Any question, guys? Okay, so thank you so much. Where is the summary? Okay, just a moment. Let's see in the summary slides. Yeah, keep. Okay, so the last slide, I don't know why it's not appearing here. Yeah, so at the summary here, guys, this is what we have discussed in this material. So we discussed the numbering systems, decimal, binary, and hexadecimal, and we understood how to convert from one to another form, the different digital gates and using of these gates in calculation, like making others, like by the same way can be used in multiplication or division or whatever. The internal structure of the microprocessor, the function of each part inside the microprocessor, how an instruction is performed inside a microprocessor, and the different architectures of processors. Okay, so this was the target of this slide, and we could cover all of these parts. Thank you so much, guys, and please, if you have any question, send me on my email. When you study, send me on my email, or you can come to my office during office hour anytime, or you can assign a meeting with me anytime. Just send me an email. Thank you so much, and see you in the next class. Yeah, have a nice evening, guys.